Okay, there we go. I'll try not to speak too loud. I know this microphone sometimes gets a little loud. So, how's assignment, what are we on, 6 now? How's that going? The thread pool? Peter? There are 8 assignments. At the end of this week, we'll have 7. That'll be due around, well, the following week. And then over Thanksgiving, unfortunately, you'll have to work on one. But it won't be due until the last possible day we can accept it, which is kind of into the following week there. So it's you've got a fair amount of time to do that. Yeah.
Is assignment 8 designed to take those full amount of weeks?
No, it's not. I wouldn't say assignment 8 is assignment 8 takes a while to get your head wrapped around, but otherwise it's not too bad. I mean, there's a lot of parts, a lot of moving parts to it, like the other assignments too, but it's not the Stanford shell in terms of there's 400 things you have to do. You have to do a couple of key things. You have to understand how. But that's about it. Yeah, Michaela.
Will there be like TAs or people on Piazza?
Yeah, there will be people active on Piazza. Yes, during the Thanksgiving break. Yeah. In case you have questions, we're not going to just disappear. But it's not going to be, go to the office hours. So yeah. You'll have some time after a break too. It's not like it's going to be due right when we get back. So, yeah, Peter. Assignment 7 is going to be due next week. Yeah, 7 I think is probably a little trickier than 8, believe it or not, even though you have a little less time. But it's I'll do an intro of it. Yep.
Sorry, quick question about that. Is it due Wednesday?
I don't know exactly which day yet. I'll look at what day it's due. Yeah, I mean I'll put that up in there. Okay, so we're getting there. We're still doing networking. Today, I wanted to to basically spend kind of most of the time going through a somewhat large-ish problem that we're gonna write, and we'll definitely test my typing skills on this one. But I'll go slow enough that you understand it. But the basic idea of the thing we're going to do is we're going to write a server that is robust enough to be the kind of server that you might find on the back end of a website serving up some stuff. Now, in particular, what we're going to serve up is going to be it's going to basically be Scrabble words, okay? So it's nothing too groundbreaking here. But basically, we have a program that will find Scrabble words. In other words, take a bunch of characters you pass into it and find the anagrams of all those characters, including all the ones from 1 character up to, I guess 2 characters is the least that are in a Scrabble dictionary. 2 characters up to the length of the number of characters you have, find all the permutations of that, and then spits them out. So let me show you that program first of all. I won't show you the details. You can look it up. It's literally like a 106B kind of assignment sort of program. But let's see, it's called Scrabble Word Finder. And then if you type in a bunch of characters, last year I typed Leyland with a Y and I got booze. So did I type it right this time? Or Leland. There we go. Now I've even said it wrong. Oh, great. Now I'm in trouble. Anyway, what it does is it finds all the words and it just spits them out. And it's just a command line program. And you can do the same thing, Scrabble Word Finder, and it will find all the words that you can make out of those. And that's all it does. It takes input on the command line, spits out the results, which is all these words. Okay, and what we're going to do is we're going to create a server that serves up these words and does a little bit more. Okay, it does a little bit more basically because servers don't always just give you back exactly the thing that you're trying to calculate. It might give you some more information. What we're basically creating here is an API, okay? An interface for this web server that we have that's going to spit out these words for us, okay? What we're actually going to do is have it spit out a little bit more information, and it's going to spit out, for instance, the time it took to perform the search to find all those words. Why might we care about that? We're probably not going to care too much about it, but maybe you have some API where you're like, oh, I want to know how long it took to do the search. Like Google might have that returned as part of their API. I mean, they actually tell it to you on the web page. Like this search took, 0.4 seconds or whatever, and you might care about that. We're also going to cache the data. In other words, many APIs work this way, where you make a request, and if someone else comes along with the exact same request within some time frame generally, it will just not bother redoing the calculation, which might take time. It will just cache it and then return the cache value to. And hopefully if you did the same one twice, Let's see. Now, this is a different example. If you do the same one twice, you'd get a much shorter time to do it, because hopefully caching, you've done it in such a way that it takes less time to pull out of the cache than it does to recalculate what you're trying to calculate. So that's nice. We're going to do this in JSON format. Who knows about JSON format? Have you seen it before? Yeah, it's a format that was originally, it stands for JavaScript Object Notation or something like that. And it was designed by a guy who did a lot of JavaScript. In fact, he wrote the book, Douglas Crockford wrote the book called JavaScript: The Good Parts, which is a necessary book. JavaScript, the whole JavaScript book is like 4 inches thick. JavaScript: The Good Parts is like half an inch thick, and you can actually do everything you need to using only the good parts of JavaScript. And anyway, he created this format saying, oh, this should be a more or less human readable format, but also machine readable, in the sense that if you format it correctly, it's easy for the computer to pick out the answer. So here's or to pick out the data. And here's what we're going to pass back. We're going to pass back a dictionary, basically a map, mapping strings, time cached, or all the possible words, to the time, to a Boolean value as to whether or not it was cached, and to the possibilities. That's what we're going to create. Once we do that, we will feed that answer back to the client, and that's the server we're going to create. Okay, questions on that? All right, so let's see. How are we going to actually leverage that program that we have written? Well, we could rewrite it and put networking into that program that spits out the words, right? We could cannibalize that program, take the program and say, okay, we're just going to make a function in it that actually does the words, and the rest of it is going to be the networking part and whatever. But that seems a little crazy if we already have a running program that uses these words, or that knows how to produce words. Why muck around with it? Right? We know it already has a good interface. You type the command line, on the command line, you have one parameter, and it spits out the words to standard out. Let's leverage the fact that the first half of this class was about creating this thing called subprocess. Let's use that, right? So we're just going to use subprocess to the function we wrote earlier to actually run this lexical word finder and build a networking program that then just calls this, or that runs this program. It seems like a better idea. If you've already got a working program, why change it? Why not just do another smaller program that utilizes that? So we'll do that. Okay? All right. Let's go and actually start building this program. It is called Scrabble Word Finder Server.cc, and this is how many inputs, this is how many includes we have. It seems like a lot, it is a lot. Why do we need them all? For the various different things we're doing, right? We're doing a lot of stuff in this program, as it turns out. And we will go through and see it. Let's start with main, and I'll describe what we're going to try to do down in main here. Okay, so remember what this program is trying to do. This program is trying to basically create a server. In that server, it's going to, we're actually going to figure out who's asking, who the client is. We're going to capture the IP address of that. We didn't do that last week when we did this. We're going to capture that. Why might you care about capturing what the IP address of the client is? There's 1,000 reasons. You might care where in the world all your users are coming from. You might care to block users that are trying to hack into the system, or users that are using your server against whatever terms of service you have, etc. So it's nice to know what the IP address is. And trust me, every website you've ever gone to in your life has basically logged your IP address and any other information it can find about you, because that's worth something. So I probably don't need to tell you that in this day and age, but your data is actually worth something. And this is one of the ways we get it. Just at least knowing where the IP, or what the IP address is, starts that ball rolling as far as gathering data. So you have to be a little careful there. Then we're going to create a thread pool. So you guys are in the middle of a thread pool assignment, but we're going to create a thread pool. Many times for servers, we want to create a thread pool. Why? Because we want to accept many clients all at once, and we might be running a process like generating anagrams, which is not a terribly fast process. And then we might do that if we do it in a thread and then allow other threads to accept more clients. That's best for our clients. Okay, so nobody has to really wait around. At least the 16, no fewer than 16 have to wait, because that's what we're going to do. And then we're going to schedule this, and then we'll write the little, we have to actually take the data and process it, and then send it back to the client. So we'll get into that. So let's start out the program here. We're going to get the port number, unsigned short, I'm going to start typing slower. I think that's where you go. Unsigned short, port equals extract port. Now there's a function up here called extract port, which basically just takes the argv that you pass into it and then takes the port number out of it and turns it into a usable port. If you give it a port that doesn't make sense, it will do that. There's also a default, so it's not the biggest deal in the world. argv1 in this case. Okay, and then we're going to create our server. Create server socket. We are going to learn about this function on Wednesday. So right now it's a little bit opaque, but we're going to learn about the function on Wednesday and see what the details are of that. Okay, and then we are going to say something like created server on, let's say listening on port, and then the port, something like that. Okay, then we can create a thread pool. So you're going to, this program today is like all the stuff we've done throughout the year. It's got threading and sub-process and all that kind of stuff in there. And then let's create a pool of, let's say, 16. And then let's create a cache. Well, how are we going to create the cache? It's going to be a mapping string to a vector of strings, because that's the words we're getting back are just going to be a vector of strings. Okay. And then if you have a data structure that you're going to have multiple threads modifying, what do you have to have? A mutex, yeah, thank you. Mutex, let's call it the cache lock. Okay, we better do that, because you have to think about these things, right? If you're doing multi-threading, you better think, oh, I've got lock, I need locks, and to deal with this. Okay, let's do a standard loop for our server. And in here, this is where we're going to try to extract the website. So I'm going to show you some details that you don't need to know now. We'll go over a little bit at the end of class today. There is a thing called a struct sockadder in address. Okay, it's an internet address basically, and a struct sockadder in, and that will be able to pull the data, hold the data for the internet address that we care about. Okay, and then we actually have to have a sock length as well. We'll call it the size equals size of address. Now, why might I not hard code these? Well, it turns out these might not be, they're well defined, but they're defined in such a way that we can change them to other different types of addresses. We'll talk about that at the end of class today as well. Okay, I'm going to do this. This B0 just zeroes out the actual socket, the address itself. I'm not sure that's 100% necessary, but basically we're going to pass in this blanked out struct. Again, I'm not sure it's necessary, but that's the way it goes. Then we're going to accept a client. What do we know about accept from last week? What does it do in particular that makes it so this while loop doesn't go forever? What does accept do? If I say int accept, and then I say server, in this case we've got struct sockadder. Well, again, we'll talk about why these are in there in a little bit. Address, oops, size. Okay, what's this going to do? Anybody remember? It's going to wait for a connection, meaning it's going to just sit here and block. This is a blocking command. This is a blocking function here that basically says, well, look, I'm just going to wait around until somebody decides they want to talk to me and sit there. So that's the blocking part of this. At the last couple days of class, we're going to talk about non-blocking networking, which is a different way of doing it where you actually don't need to block on this. And you can set accept to not block, much like you can say to wait PID, don't block. It's a similar sort of idea where you can do it. And you may have various reasons for wanting to do that. Okay, once we do the accept, we're going to have this address we need to get it into a form that we care about. In this case, we're going to do it into inet addr stir len. That happens to be a constant that says here's the biggest an internet address can be. So we could have said, 26 or whatever, how many characters it happens to be, but It's a constant that's built there. Okay, and then once we have that, we can say cout, and we haven't done anything. We haven't done anything with this quite yet, but we will. Cout, and then received a connection from, or a connection request, we should say, request from. Okay, and then let's do it this way. There's a function called inetop. What's that all about? We'll look that up in a minute. And there's some more constants in here. Again, we'll talk about these in a few minutes. Address dot internet address. That's one of the fields in there. Inet addr sterlen, like that. And L. Oops. There we go. Okay, what have we just done there? We have now used a function that's gotten the address and put it into a format that can be printable. So what is an IP address? Well, it's a number, actually. It's a 32-bit number. In fact, there's 4 different fields to it, 4 bytes in it, and that number needs to be converted into an actual, because it's a binary number. It's not like a number it's just a binary number of the 4 parts of your IP address, and inet_ntop actually converts that into a string for you. So lots of little things that happen. And again, we'll talk about this part at the end of the class. Okay, once we have done that, now we can actually, we've got the IP, we've said, hey, I've got a connection. Let's actually schedule the trying to produce those words. Pool.schedule, okay, client. This is going to be a Lambda function. Client, we're going to pass in this cache that we created, and we're going to also pass in the cache lock, of course. Okay, and then in here, let's do publish Scrabble words. We'll go write this function in a minute. Scrabble words, client, cache, and cache lock, like that. Okay, and that should do it. Okay, and that's all we need to do. So that's our main function for the server. Yeah.
189, is that supposed to say address dot in Azure or sin Azure?
It is actually supposed to say SIN. I think it might, I'm not sure what that, actually, let's look it up. Let's see, this is a struct sockadder in. And struct, of course, I just forgot what it was. Struct, what was it again? Hang on. There, let's see, where is it here? Sockadder, there we go. Struct sockadder in. Okay, man, there we go. Oh, not there. Man, except, let's see. Let's see if it has in here. Man2 except, maybe? There we go, struct sockadder. Does it say this structure is filled with the address of the peer socket? The exact format is determined by the socket's address family. So it has to do with the family of the type of address. In this case, this is a IP version 4 address, which is the regular IP addresses that you've seen before. We'll go through that a little bit more in detail at the end. Yeah, so thank you for trying to catch that, though, that bug there. Okay, other questions on what we're doing here? Basically setup. Yeah. What is client? So actually this should probably say client here, shouldn't it? There we go, thank you. Equals, there we go, yeah. That make more sense? Now we're going to actually get the client is the file descriptor for the client socket that we're now that we've now gotten from the accept. Yeah.
Right, so could you just explain like one more time like what's going on in like the first argument of the accept call?
Right here, well, that should also, thank you for pointing that out. That should be a comma. There you go. Yeah, so it's just, it's trying to, it's accepting from, before we had accept server null before when we did it last week, but now it's just, it's saying, hey, accept a connection on this, based for this server. Here's the details to put the IP address into. Yep.
In 177, is that where server is shared, or?
That's where, yeah, what am I doing? I think I'm losing it here. You just need to keep me honest. How's that? Thank you. That would have been an ugly bug to fix too. Okay, does that fix it? Now there's where the server is actually being created. Yeah. Okay. All right, so we've got main done now. Now let's actually go up and look at this publish Scrabble words function, because this is going to be a pretty decent sized function as it turns out. In fact, I'll go over to the top because it's going to be a pretty decent sized function because it has to do a few things here. It has to set up the buffer. It has to get the details from the client, like what letters do you want to actually produce. It has to check the cache to see if the letters are already mapped into that cache. It's got to update the cache if we don't do that, and so it's got to do a few different things there. And so we'll go through this relatively slowly, but we'll see what it does. But it's doing a bunch of things here. Okay, so what have we passed in? We've passed in the client, we've passed in the cache, and we've passed in the cache lock. So the first thing let's do is let's create a sock buffer for the client, okay? And we'll do it this way, SB. And that sock buffer is going to be that's a class that allows you to not have to worry about all that while looping around write or reads and so forth. So that's nice. And then in fact, we're going to make it even nicer. We're going to do an IO sock stream. An IO sock stream, which is the actual class that allows you to now write and read to it using the angle brackets, which is kind of nice. Okay. All right, once we do that, let's actually call a function we'll write in a second called getLetters. And the getLetters is going to use that stream to input all those letters for us, okay, from the client. Okay, once we have those letters, so it turns out we're finding anagrams, so we're getting a whole bunch of letters. It doesn't actually matter what orders those letters come in as far as doing the anagrams. So let's actually sort them. This is going to be useful for the cache. Letters.end. Okay, so once we sort them, then we can, I guess we could have done this in any order, but let's actually skip the headers, which we wrote last week. I'll show you that one again, but it's not, that's basically saying, okay, we've gotten the letters, let's skip the rest of it because I'm about to send data back, and we want to basically clear out any input from the buffer before we start shooting stuff back to the client. Okay, so that's kind of necessary there. Okay, once we do that, we're going to time this, right? We're going to time how long it takes. There's another type of variable called a struct time val, which is, in this case, we're just going to call it start. And then what we're going to do is we're going to call a function called get time of day. And it is going to pass in start, and then turns out there's another parameter we're not going to worry about. And this is starting the clock because we're about to say how long is it going to take us to do this query. I suppose we could have done this a little higher if we wanted to be actually, extra precise about it, but in this case we're going to do that. And then once we do this, well, now we're going to check our cache because we might have had this in our cache. Remember, we don't know what state our cache is in at this point. We're going to do cache lock, and then we're going to check it, right? So what are we going to do? How many people in your last assignment or this assignment are typing auto and then like something else and they get all confused about that? You should probably try to figure out what your return types are if you can. Sometimes it's a little confusing. In this case, we're going to find out of a map. So what we want is a map of string to a vector of strings, and then this is actually an iterator, as it turns out, which basically returns just a pair, but this you should probably at least know what it is that you're trying to do here. Found equals cache.find letters. So we've already sorted them, so that's it, and this is going to be a pair. Okay, so what have we done? We've now captured the letters. We've gotten out of the cache if it's in the cache, so we don't have to go use them again. The first time through, of course, it's not going to do anything here. Let's actually check and see if we've got dual cached equals whether or not we found it or not. So if found is equal to, let's see, how about if found is not equal in this case to cache.end, that will end, okay? That will tell us whether or not we have gotten to the end of our, or if we have not found the letters in there. Okay, so now we've got a Boolean value that says whether or not it's cached or not. Okay, and then let's create our word vector, because we're definitely going to have to get that out of there. Vector of strings, word vector, or let's call it formable words. Formable words. Okay, if we found this in the cache, what are we going to do? We're going to actually pull it out of the cache. Okay, well, we've already done that, as it turns out. Formable words equals found, and this is because this is a pair, it's the second part of the pair here. Okay, if it wasn't cached, well, now we have to actually go and find it in the actual word. So we have to do a sub-process. Okay, remember, see how this is like, oh, we've got more stuff to do. Question?
Shouldn't it be cached for the if condition since a Boolean and
Yes, thank you. If we've cached, there we go. That would probably not be good either. It would always try to do that. Yeah, okay, good. Any other comments on that? Okay, so let's do the sub-process. Back to the sub-process. This is like review day, I guess, in that sense. Okay, so what are we going to do here? Const char, let's see, we're going to do const char command, and our command is going to be / scrabble word finder, because that's the program we're going to run. We have to pass in the letters, but it has to be a C string, as it turns out, because of the way that works. And then we're going to make sure that we null terminate our command argument list. This should look familiar from the subprocess. Then we're going to have subprocess _t sp equals subprocess const cast, and then char * command, and then false and true. Anybody remember what false and true mean from their subprocess? False, the first one means we're not going to send any more data to it. We're actually doing that in terms of the letters. And the true means we're going to ingest from the file descriptor that we get back. So we're going to do that. Okay, and then once we have that, then we can say, oh, okay, pull formable words. This is another function we're going to write. Pull formable words, sp ingest fd, and then of course we're going to wait PID. We can't forget to wait PID. How about wait PID? We're going to do that, and then we're going to wait on our sp.pid. We don't care about the return value, and we actually do want to wait for it. Okay. All right, and then at the end, once we've gotten the data, if we went and did all this work to look it up, what should we do with that data before we send it back? Cache it. Let's do that. If we're going to be doing the cache, we better have either lock or do a lock guard around the actual data structure. Okay, and then once we do that, now we can just put it into the cache.
You already locked it.
Did I forget to unlock it? I did. We can unlock it right after we find it. Thank you. Why can we do that? Turns out that it doesn't matter. Once the iterator is going to be fine, we're not going to actually be modifying anything. The iterator is actually going to be fine, so we don't need to keep the data structure locked. Good call. Okay. All right, and then finally we're going to have the cache letters, which are going to be the formable words that we just got out. Okay, and that's really about it. Yeah.
What happens if like something got deleted from the map?
Almost it. If something got deleted from the map, at what point?
After you unlocked it, if someone deleted whatever your iterator, say you were looking for like Leland,
Yeah.
and someone deleted that entry, would it still be okay?
Yeah, this is a good question. If you have an iterator and under the hood somebody removes that from the map, that's probably not a good thing. In our case, because we know we're only adding to this cache, it's okay. But you do have to think about that sort of thing. Yeah. I think the iterator in that case would probably be bad if you tried to go grab the data after it's been removed. That's my guess. Yeah.
So like, what happens if it doesn't find it, and then in between like unlocking it and trying to get somebody like adds it into something else?
If someone adds another one, it won't be, it will be fine in this case, yeah. As it turns out, it's fine. Because it's a reference, the underlying data structure, and you might need to know this, I guess, about the underlying data structure, but it's not going to delete and read, like it might move that around in some form, but the reference to that vector is still going to remain the same. The reference to the vector is going to remain the same. Yeah?
Does cache.end change as cache changes, or is that the same?
Does cache.end change? Cache.end, let's see, that's a good question. I don't think cache.end will change for our iterator, the one that we've created. I don't believe it will.
I mean, if you have a vector, right?
No, I understand. If you have a vector, is the end gonna change? Well, it's a map, remember?
I don't understand.
Right.
I'm just
Oh.
wondering in general for
Yeah, that's a good question. I think that you will immediately be able to tell. I don't think it will matter. I'll have to check on that. I'm not 100% sure. Good. This is a good question. The question is, can you unlock it there before you've even checked to see if it's the end? Not 100% sure in this case. Yeah, Peter. I think you can. I think you can as well. Let me just check on it. Remind me. Or put something on Piazza or shoot me an email. Shoot me an email and we'll take a look. Okay, so once we've done this, we have succeeded in getting our formidable words, our formable words. They might be formidable, but we're getting our formable words. And then we're going to have to do, we have to finish the timer part. We haven't finished the timer yet. So let's do another couple of time values. We'll call it the end, and then also the duration, because that's the one we really care about. It's just going to be 2 values there. We're going to call get time of day again. And in this case, now we're going to pass in the end. Okay, and this is going to stop the clock. And in this case, stopping the clock is saying, okay, we've now finished up how long it took to actually do this processing. Okay, and then once we do that, there's another function that you may not have known about, but it's called timer sub, which takes in an end and a start and somewhere to put it, the duration, because this is something that people want to do a lot. Let me move this down here. And then once we do that, we can actually convert it to the time to an actual value, but you got to do another little thing here. It's duration. Duration is also a time val, which has 2 fields in it. It has a number of seconds, and it has a number of milliseconds, microseconds, that we've got to divide by 1, 2, 3, 4, 5, 6 to get the actual value. So basically, we're taking the seconds plus the microseconds turned into seconds, and that's going to be our time. And this is what we can then pass back to the client. Okay, that seems like a lot of work, and we're still in the middle. It's still in this function. We're not quite done yet. What we're going to do is we're going to create an O string stream for our payload, because now that we've got all the details, we have the time, we have whether or not it was cached or not, and we have the actual vector of strings. Now we need to create that payload. So we're going to do that. I'm going to call a function we're going to see in a second called construct payload. And we're going to pass in formable words, and we're going to pass in whether or not it was cached or not, and the time and the payload. And that's going to create that for us. And then finally, the last thing we need to do in this function is going to be to send our response. Because we've done all this gathering of data and producing all the different variables we need and all the different data and payload and so forth. Now we need to actually shoot the payload to the client. Okay, so back and forth here. Okay, questions on that function? There's a lot going on there. Yeah.
Is there a way to do formable words so you're not copying it when you do that found a second?
Is there a way to do, say again?
My understanding is that we copy formable words, like the whole vector, right?
Oh yeah.
Referencing it. Is there a way to, because like, Is there a way to do that so you don't copy it?
So you don't copy it. If you don't, is there a way to do it so you don't copy formable words? Maybe. Yeah, I mean, it might be. It's probably still once it's in your cache, you could take out a reference to that probably and be okay. Yeah, it's not the biggest, probably not the biggest deal in the world, but yeah, that's something you might want to consider if you're trying to make it efficient, make it super efficient. Yeah, good question. Yeah, sure.
Why do you choose to do the lock guard instead of just like
Yeah, good question. The question was, wait, why am I doing this lock guard up here instead of the, where did we do it here? We did it, guard, there it is. Why are we doing it right there? It's just, it makes it so we don't have to remember to unlock it. That's all. And it will go out of scope by the time it gets to here. So it just saves us a little bit of thinking in that sense. Yeah. Okay. All right, other questions on what we're doing there? These were the two biggest functions that we had to write. Yeah, Sam. Construct payload is going to take the formable words vector, it's going to take the cached Boolean, it's going to take the time double, and it's going to convert it into that JSON string that we're going to then send back to the client. Okay, we'll see that one in a second. Okay, so that's that. Let's look at the pull formable words function, which is actually not too bad a function as it turns out. So it uses fancy schmancy. We're going to look at it using fancy schmancy C++ stuff. Let me show you that. stdio, actually I think it's, yeah, I guess it is fancy C++ stuff. stdio file buff char in buff ingest fd ios : in. And you're like, what is that? Right? I'd never seen this before in my life before I saw this example. Okay, let's look up some of these things. stdio underscore file buff. stdio underscore file buff. If you look that up, it says, okay, class reference. Ooh, that's a good sign. Let's make this a little bigger. Okay, so in this it says, and of course they don't describe what it is until way down here. There it is. The GNU extension provides extensions for working with standard C file stars, not what we're looking for, and POSIX file descriptors. Aha! We have a file descriptor, which is this client that we're trying to deal with. Okay, or actually in this case, sorry, it's not even a client. In this case, it's the words from the ingest file descriptor that has come out of our sub-process. Okay, and then it says, okay, it must be instantiated with a type of character like this. Ooh, that's exactly what we did, so that's good. And then down here, let's look at the constructor. Takes a file descriptor, good. It takes this mode, and what do we have for our mode? iOS : in. And then it says, we'll look that up in a second. Then it says it takes a size t, which is a size of the buffer, which we probably don't care about. And the good news is that it's got a default value to it. Now, why am I showing you this? Because sometimes you'll find code when you're reading code, and this happens all the time, and you'll see something, you'll go, I've never seen that before. And you've got to go be able to look this stuff up and actually figure it out if you want. I mean, you can ignore it and be like, hopefully it works. But if you want to know what it's doing, or you want to know how to do something, you have to be able to look this stuff up. And this one was iOS : in. Let's see, what is this? Input. What is iOS in and iOS out? Oh, that's good. Thank you, Stack Overflow. What's it say? It says iOS in allows input from a stream. Oh, good. We're trying to do input. That does it. And then it says it's a bitwise used to combine the two flags. Oh, good. They're flags. Probably what we're looking for. Okay. So that's that. So once we create that, then it's just a matter of turning it into an iStream, which is we've used that. Okay. Again, this whole file buff thing was so that we don't have to read and write or read in some while loop. It does it for us. And then we can create it. Once you have a buffer, you can convert it into an input stream. While true, we're going to simply read each word, string word, and then get line, is in the word. In other words, reading in the words. If is fail, in other words, we've gotten to the end, break out of this while loop, and then let's add it to our formable words. Formable words dot push back word. Okay, that's it. So that's our whole function. It's just going to read in from the output. Okay, so we've done that. Let's look at, let's see, have we done get letters yet? I think that was one of the first things we did was to get the letters from in the main. Let's actually look at that one right now. To get the letters, okay, we passed in a stream already, so that's nice. We can then just say something like string method, path, and protocol. Okay, remember from last week, we are trying to get a request, the details of this request from the client. So the client is going to send us a well-formed, hopefully, well-formed request. What does that look like in this case? Well, first I'll just do it like this. We're going to get the method, then we're going to get the path, then we're going to get the protocol, and this will look something like this. This should look familiar from last week. Get slash ABCDE and then HTTP slash 1.1, something like that. And we're going to just get those out of the request. Okay? Again, why are we going through all this in such detail? These are the kinds of things you have to think about when you're doing a low-level server like this. Okay, you have to think about, oh, now I've got to get the data out of here. We also have to get the rest of the line if there happens to be any more of the line. So let's do it this way. Rest, get the rest of the line. And this we're just going to throw away as it turns out. And then we're just going to basically find the position of the trailing slash path.writeFind. We did this last week as well. Of the trailing slash. And then we're going to return the string that we found. Okay, how are we going to do that? Well, we're first going to see if the position is didn't find that slash, in which case we just return everything in the actual path, because that's the only thing we were given, as it turns out. So this is string npos, which means we didn't find it. Path, then we're going to return the whole path. Otherwise, we're going to do the path substring of the position plus 1, which is the rest of the string past the star. That will give us the ABCDE, like that. Okay? We're getting there. I know this is a lot of code for today. We're getting there. Okay, we saw a skip headers thing. This was the same thing we did before. Basically skip all the lines as the headers. We don't care about the headers for our program. You might if you were doing that. Let's see. We've got a construct payload. There's a construct JSON array, which is, again, a lot of stuff you have to think about if you're writing this stuff in C++. But the construct payload basically is creating that JSON string. And it's a little bit of code here that just creates it by putting quotes around the right place and whatever and constructing that string. Okay, that is actually all the code we need to write for this. Did anybody see any bugs? The odds this compiled is about 0.0001. But let's try it. Make Scrabble word finder server. And, oh, what? Did it work? Wow, okay. Thank you for finding the bugs earlier. Hopefully there was not a bug that didn't make sense. But let's try it. Server, it's called Scrabble, Scrabble word finder server. Okay, and if we run this and we are on myth 59, if we're on myth 59, we should be able to telnet into myth 59 on port 13133, and it should connect, and it did. And if you take a look down here, it says receive your connection request from, that's our IP address on, what am I on there, myth 66. So that actually works. So far so good. So we can now say something like get slash LEAND and HTTP slash 1.1. Again, that part's actually ignored. We could say anything there because of the way our program's written, right? And then we have one more blank line and nothing happened. So what happened here? Get Leland, HTTP.
I think he wrote send response.
Oh, I didn't write send response? Oh, maybe that's what happened. Did we not look at send response? Oh, well, at least it did everything up to that point. We don't know if it did anything else. But let's see, send response. Oh, look at that. Thank you very much, Grace. Okay, so let's actually figure out how to send the response. Okay, this is actually this is one of the more interesting parts about this. I guess I'm not surprised I forgot to do it, but here's what we need to do. We need to send a response. We haven't talked about what a response looks like. Well, a response has a a few specific things in it. 1.1, it said the first thing you should get back is like the type of HTTP protocol you're talking on. And then you have a number here, and then in this case it's 200 and then OK. Believe it or not, you say OK in every response, /n, and that is a HTTP status code, 200. Okay, I want to look this up for a second because let's look this up. HTTP status codes. Okay, let's make this a little bigger. There we go. HTTP status codes on Wikipedia. So these are all the status codes, and these are the codes you need to send back if you are sending HTTP. If you have a request and you want to send back a response, you should do this. They go 1, informational, 2 is successful. We sent 200, so that means we are successful. That's good. There's other different variables. 300 is redirection, 400 is client error, 500 is server error. In fact, there's a easier way to remember this, or at least there's something somebody put together. Where is it? There it is. This is what they stand for. 1 is hold on, you gotta wait for me for a second. 2 is here you go, 3 is go away. 4 is I screwed up, and 5 is you screwed up. Or sorry, 4 is you screwed up, and 5 is I screwed up. And those are the ones that we actually, you will see. So if you ever see one that's 5xx, it means the server messed up. If you see a 4xx, it means you messed up. Let's look at some of these ones. So the 100s are things like continue, which means, hey, you got to wait a little bit for some things for me to do it. I'm not sure what early hints is. Success is 200 means, oh, okay, here's the response, and we're about to create that. Created is there's some new resource that got created. I don't know when you would necessarily use that. No content if you didn't have any response, but it was still a good thing. Redirection. This is where if you're asking for a particular web page and the server says, no, it lives over here. That's nice when you're changing the underlying web page and you want to be able to redirect people there. Found, see other. Let's see, here's some client errors. Bad request means you didn't send something properly formatted. Unauthorized basically means, hey, you needed to log in and you didn't. Payment required. Reserved for future use. That scares me a little bit. Right? There's one that's good. Supposedly Google uses this one, but you don't need to use this one. It's not technically a real one yet. Forbidden means you don't even have access to that. Not found, 404, that's a pretty classic one. Means you tried to go to a website and it came up and goes, I don't know. So you've probably seen 404 before. Let's see, gone means that it's what you maybe used to be there, but not anymore. Let's see, how about 418? I'm a teapot. That one was defined 1998 as one of the April Fool's jokes. So technically it's not really real, but I guess basically if you were to go to that website and request coffee and it happened to be a teapot, it was supposed to respond with 418. I guess that's a joke or whatever. Turned out one of the first web servers was actually for a coffee pot. You could actually query it and it would tell you whether or not the coffee was brewed or not, or how long ago it was brewed. So I guess that's probably an inside joke there. That was an Easter egg from 1998, so relatively old. Let's see, 451, unavailable for legal reasons. Maybe you have to respond to that if you are told by your government or something to do that. And the code is 451, as in Fahrenheit 451. So, some people have good senses of humor about these things, or some sense of humor anyway, whether they're good or not. And then you've got the 500s, which are like the server problem. Occasionally you'll see things like that, like internal server error. It means somebody screwed up on the website itself and the server, and they couldn't respond to it correctly. And so there's lots of ones in there. Okay, so let's go finish this up. So we have the status code, and then after that, you have to tell the client what type of data you're about to return. And it's content type, and it is content type application /JSON. You could actually say application /JavaScript as well. And then if you're being nice about it, you'll say the character set, which is basically saying, hey, I don't just care about like English and America and so forth. I care about the rest of the world, so I'm going to send my response in a format that is universal, UTF-8, which is Unicode format. And then after you do that, then you have to send how much data you're going to send. Content length. These are all headers, by the way, just content length. And then let's send the actual payload size. And this is nice. This is actually a regular old number, as it turns out. That's nice that you don't have to format it any other way. And then after you do that, you're done with your headers. You have to send a blank line, /r/n, and then you can finally send the payload. Payload, and then don't forget to flush. Okay, after that. All right, and that would send the response. Yes, sure.
If you did an endo, would that send?
Yeah, good question. If you did end-L, it would probably just send the \n. Web servers generally expect a \r and a \n, although these days many of them are probably robust enough not to worry too much about it. Yeah, good question. Yeah.
So wait, is the application/JSON and the try set, and those like both like part of the value for like
This is part of the content type header. Yes, application JSON and the char set UTF, that's part of the content type. You probably could do them on two different lines if you wanted to, but in this case I think it's probably the format you may not be able to, but it probably just says, hey look, you're going to do the content, you put a semicolon, it just says what the encoding is for it. Yeah,
Is it like standard to hard code that 200 okay, or is there a way to make that more generic just in case?
Yeah, the question was, do you want to hard code it all the time? You don't have to. In fact, your next assignment proxy server, there are going to be times where you'll send an error message through that header. So yeah, you wouldn't, I mean, in our case, we're going to just respond to it because we don't have anything else. We haven't done any error checking in that sense. But yeah, if the page wasn't found or something, the server generally sends these for you. Like if the server can't find your page, it's the one sending those codes. Okay, but you can, of course, put your own headers in there. Okay, let's try this again and see if we can do this again. Okay, listening, telnet. Did I forget to make it? It's like I don't even know how to program. Okay, there we go. All right, thank you. Okay, there we go. All right, telnet, there. Now we're there. Get/abcde http /1.1 and no. Oh no. Let's see. So it connected okay. Looks like now we would have to go and see what the issue is. I'm wondering what the best idea to do. I should just do it like last time and say it's close enough. But because I don't know where I would go and start to even debug this one. It could be in a couple different places. All right, I'm going to do a bad thing. I'm going to do the same thing I did before. Scrabble Finder original. You saw all the code. Now you can find out you can actually look this one up to scrabblewordfinder.cc. Oh, I hate it when that happens. Okay, let's make it again. And then let's see if this one works now. Watch, it'll just be something that I did wrong in the telnet. Oh, I know. You know what? I bet it is. What's that? A blank line. Yeah, that's probably what it is. Oh well, too late. Oh, here, look. Yeah, it needs a blank line. Hang on. Is that the one? Yes. Quit. I'm telling. Okay. All right. We'll see. How about this? Luckily, scrabblewordfinder.cc is the old one. We'll try it again. Wordfinder.cc. Yeah. Let's see. Scrabblewordfinder. Sorry. Scrabblewordfinder server.cc. Scrabblewordfinder-server.cc. Okay. Yes. Make. Okay. Run it again. If it still doesn't work, I'm going to really look bad. Oh well. Okay. Been there before. Okay. Get/abcde http /1.1. Well, it doesn't matter. We ignored it anyway. It still didn't work. Okay, hold on. What's that?
Did you get the original file and the?
I can do. I could do. Well, actually, I added some other. I added slightly different things to the original file. It doesn't look like it's actually returning the response correctly. So, all right. I have a feeling it's not. Maybe something's wrong. They're wrong with our sub process thing or not. We'll try this one again.
It looks like the last time you typed it, it just typed HTT and not.
That's okay. We ignored that part anyway, the HTTP part, because Word's our server, so we don't really care. We ignored that anyway. Good thought. Thank you for, let's see, that's not, okay. Yeah, oh no. Server. Okay. Yes. And make Scrabble word finder server. I didn't, hang on. Make Scrabble word finder server. Okay. Did I screw up our Scrabble word finder itself program?
Do you want to do Scrabble
No,
word
it's all right.
finder orig server? Like you copied orig
Oh.
into server.
Okay, thank you. How about that? Oop.
Is the server
Oh. Oh boy. All right. It's been a long day. Okay, hold on. Yes, go ahead.
I was gonna say a difference I noticed from the slides is
Uh-huh.
when you're declaring subprocess, or when you're declaring a command for subprocess and publish Scrabble words, you did car star command instead of car star command, which is written.
That should have gotten an error, but that might be it. I'll check. I'll figure it out and put something on Piazza, but find my screw up if I can. Okay, let's make it again, and then let's run it again. Scrabble word finder server. Okay, and then there's that, and okay, get /abcde http/1.1, and then there we go. Okay. All right. Yeah. Well, don't give me too much credit for that. Okay. So anyway, here's what we got back. Okay, we got back a nice, well-formatted response, and we got the JSON there. Okay. Now, what's nice about this is we did this in such a way, or at least we should have done this in such a way, that we can actually go to a website, and in fact, I have this on the slides, and I'll go to it. Let's see, there it is. We can actually build a little website that looks at it. If you've never seen HTTP or HTML or JavaScript before, don't worry about it. But basically, there's a little bit of HTTP up here, which sets up a little web form, and then has a little JavaScript to actually do a fetch from our program. Okay, and I happen to have put this on cs110.stanford.edu Scrabble word finder, like that, and oh no, is it Scrabble word, oh not dot finder, how about dash finder, there we go. Okay, actually let's do this, now I think about it, I want to do it in Chrome because I happen to know the tools there better, so I want to show you one other thing. So here's what it is, and if I'm going to pull up what's called the developer console, which pulls up in fact, I think I can make this bigger. There we go. Okay, it'll have an error if we have some errors in this. So if I type like that and I submit it, okay, it says access to fetch from blah 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 has been blocked by some policy, and unfortunately, it doesn't tell us the actual thing, but it says there is no access control allow origin header. I had to look this up. It turns out that we're running on Myth 59, and on the web server for Stanford is on a different computer altogether, in a different domain, as it turns out. And browsers these days won't let a web page by default pull from another web page behind the scenes because it might not be pulling from the web page that you want. In fact, it certainly won't let you do, if you have the little the lock up in the left corner, it won't let you pull from an unlock or a non-encrypted page. But it's good enough that there's some security in here. So I had to look up what we had to do, and here's what we have to do. Then Scrabble word finder server. And let's see, I want to look for this line right here. So before we do the content type, we have to send another header, which is this header that says access control allow origin http web.stanford.edu, because I know that's where we're going to, so I can just do it this way, r/n. Like that. So now we will be able to have that header sent so that the browser goes, oh, okay, that you're trying to pull from this website, which is a different one than you're on, but the one that you're pulling from says it's okay to pull from this website, so it's actually okay. So let's see if that works. And Scrabble word finder server. And then if we go back to here and we submit again, let's actually clear out this message here. If we submit again, then, oh no, oh, I know what happened. Oh, I do know what happened. Here's what happened. This is one of the reasons I should have put this in here. I know what happened here. Don't worry, I'll fix it. Trust me, I do know just about what happened here. This is from here. Let's see. This needs to be, that needs to be in, let's see. Which one was that? That was construct payload. Construct payload, which is here. And, okay. There we go. Okay. Notice how time and cached don't have quotes around them. Turns out they have to. I had to look. Hang on. There we go. Oh. Nope. Why did it do that? Hold on. There we go. Okay. Hold on. Undo. There we go. We'll copy this whole thing here, and there we go. Okay. So we've got that whole thing there, which we want to put the. Now we've got the little the ones in there that we need, and we're not going to worry about that one. And let's see. This is the one we want to there. Why do I have this feeling this is not going to quite do it? That's there. Okay, and then I believe we may also have to do this. We have to put actual quotes around. We have to put actual quotes around the JSON strings as well, which should do it there. Okay. Now, let's grab word finder, request. Oh, it's other people. Are you getting it? Who are the people who are trying to go through it? Are you getting it? Hopefully you're getting it. Let's see. If we submit it there, there we go. Okay. So what did this whole website do? I know. What did this website do? Let's refresh it and try again. The letters that we send in, if we send in something like that, we can submit it, and it says that took 0.04 seconds, and then it found all the words that we could make from the letters in Stanford. And then if we try it again, it should be cached if everything works right, and it should if we submit it again. There we go. It took 0.0004 because it didn't have to go create all those. Okay? All right. Whew. That was a lot of stuff that didn't go quite as planned, but that's the way it goes. Questions on that? What have we done? We've created we've created this server that allows you to go and read actually like an API that you might find in anything. Yeah, sure. Yeah.
Interrupt your server, right? And then you start it again.
Yeah, good question. If I interrupt the server, if I go over here and go, sorry, whoever's trying to request it, if I go and do that, then it should say problem.
Does the cache go away if you start it again?
Oh, the cache goes away as well. Yeah, I could have saved it to the disk if we wanted to, but that seems, we could have done that, and then every time we load the program up, load all the cached ones. It depends on what you do. When a cache has nothing in it, it's to be said to be cold. A cold cache means there's nothing in it yet. After it's been running a while and you start getting lots of requests that are cached, it's said to be a hot cache. And you want your cache to be hot because it's going to be faster in general. Question?
How come when we telnet it, can close the connection after?
Oh, good question. How come when we telnetted it closed the connection after we did it? HTTP 1.1 actually closes the connection after each request. Even this one it closed it after the request. Every time you make a request, it opens up a new connection. Now, they've changed it for newer versions of HTTP so that you can leave a request open because many programs, think about something like Google Drive, where you have a document open and there's people all over the world changing it right now. It's nice if your browser doesn't have to resend another connection request each time. So, in our case, we're using a slightly older one that does not keep the request open, but we could have changed it so it would have done that. We would have had to change our server to accept that as well, because our server expects that it's closed after we make one request. Good question. All right. Anybody else, other questions on that? Go look online and see what the actual code looks like, and you can see how it goes. For the last few minutes, I wanted to talk about some of the details of internet addresses. Okay, and by the way, that's the web page. We so far are talking about IP version 4. Okay, IP version 4 are IP addresses that you've probably seen before if you've spent any time using the internet before. And they look like this, 31.13.75.17. And there are two actually deprecated functions, but they're still used enough that I might as well show them to you, called getHostByName and getHostByAddress, which you can use to get a host based on a name or an IP address, which is kind of nice because maybe you want one or the other. Humans might want to type in www.facebook.com. Computers might care 31.13.75.17, etc. Okay. GetHostByName is a function that just requires a host name, in this case google.com, www.google.com. GetHostByAddress assumes a number that's in binary format, so it doesn't have the 171.64. It just has 171, 64, 64, and 137. It turns out this has to be in network byte order, which is big endian. If you remember from 107 what big endian means, it means that the big end of the number is first. Okay, that's kind of what it means when you're sending these. And in this case, that would mean that if you were sending 171.64.64.137, the first byte that would get sent is the 171, then the 64, then the 64, 137. This is not the order that it's actually held in memory on your computer. Why? Because Intel at some point made the decision to do everything little endian, and it means that internally you have to make a translation before you just shoot that number off to the network. Now, why do we have to make that translation? Because networks, they all have to communicate, meaning they had to make a standard for their network. They happen to choose big endian at some point. Somebody made that decision in the 1970s or whatever, and and so now we've got it. Why did Intel make the decision differently for their computer? Who knows? It's all up to the designer. But anyway, the point is that we have to send it in that form, and you'd better be able to do that. Okay? So the second part of this, the second argument for getHostByAddress is going to be the length of the address. In other words, how many bytes it is. You would think, oh, why isn't it just always 4? Well, it turns out that there's other kinds of IP addresses. In particular, there's IP version 6, which is a much better long-term solution to IP addresses. In fact, this is on a different slide, but with 4 bytes, right? With 4 bytes, how many bits is that? 32 bits, meaning you can get how many numbers. This is the exact same discussion we had, by the way, about the time last week. How many different IP addresses can you have? 2 to the 32, as it turns out, it's actually, it's an unsigned number, so you get 2 to the 32 in this case, which is 4 billion IP addresses. Who thinks there's only 4 billion computers in the world now? Right? You'd think, oh, maybe there are many more than 4 billion computers in the world at this point. So it turns out we have run out of IP version 4 addresses. What have we done about that? When you connect your laptop to the Wi-Fi, it gives you an address that's generally something like 10.something.something.something or 192.something.something. That's a local internet address for the router and not for the World Wide Web. So if someone wants to connect to your computer itself, it has to go through a bunch of kind of hops to get direct, or well, it always has to go through hops, but it can't access it directly. There has to be some translation in there. The good news is that works relatively effectively, but there's a lot of computers that we would like to give world addressable IP addresses that we can't because of the limitations of the 32-bit address. So what have we done? Of course, we've made it a 64-bit address now, which is IPv version 6. I don't know what happened to IP version 5. Disappeared somewhere, but maybe it was a testing one or something like that. But IP version 6 is the one that's 64 bits, which allows you, I think I looked it up, and it basically allows you to give every proton in the universe its own IP address or something like that. I mean, it's something like every human could have 6 billion IP addresses for themselves if they wanted this. I mean, it's plenty. Famous last words. Yeah.
Does that mean each of the numbers can be bigger, or it just has more numbers?
It has more numbers. They're still bytes. These are just bytes, by the way, 0 to 255. That's why you see these IP addresses. You're like, wait, what's the deal with those numbers? They cap out at 255, so they're just bytes. Why aren't they in hex? They probably figured the humans who are going to be reading IP addresses may not know hex or care about it, so they just made it into decimal numbers.
So how many bytes is it?
It is now, I forget exactly, I think it's 64 bits, I believe, but IPv6 is, where is it here? It's 128 bits, so I'm wrong. It's 128 bits, which is 3.4 times 10 to the 38 addresses, right? Which is a lot. 2 to the 128, which is, 10 to the 38 is roughly the number of, I think I looked it up, protons in the universe or something like that. So, or in the galaxy or something like that. It's a lot. 128 bits. The problem, in my opinion, of IPv6 is it's not easy to parse. They put all these colons in there. They allow you to, any zeros that are in order or whatever, you just have to put colons instead of the zeros, and it makes it a lot harder to read, although the numbers are now 4 times as long, so it's not easy to read anyway. So it'll make parsing the numbers for humans a little harder in the future, but you probably won't have to, as it turns out. Okay. Other questions on that? Just kind of a little side note that we'll talk about in a minute. Okay, last thing I just want to talk about, and then I think Phil will pick up on this on Wednesday. There is a struct called struct host ent, which basically has the details of what a particular host that you're looking up, what its details are. So you could go and look up, for instance, a google.com, and it may give you a bunch of different IP addresses based on something to do with the where their main kind of hubs are. Or you could look, and you can get all that information out of this business. The last thing I'll point out before I let you go, the only thing that's interesting about this, other than it's got a bunch of data in it, there's a char star star h ADR list. Not that important right now, except it's a list of IP addresses, which are numbers, and it's a char star star, and you might be scratching yourself like, wait, does that mean it's a bunch of pointers to strings because they're char stars? Or if we don't really know what that is, why isn't it void star? I looked it up. It turns out that this definition for host ent is actually predates void star. That's how long this one is. So this was way back in the in the 70s or whatever. They came up with this struct, and they didn't even have void star at that point. That's what everything was, just char star if you didn't have void star. So that was one of the reasons, at least, that they did it this way. Okay, I think that's enough for today. I think there's more details, but I think brains are probably fried. Let's talk more about this Wednesday, and we will see you then.